How can you monitor the voyage plan? The final required phase of voyage planning is monitoring, checking the position of the ship to ensure it remains a safe distance from danger areas. Why is monitoring important in voyage planning? Monitoring is checking the position of the vessel by all available means, to ensure it remains within safe distance from any hazardous areas. Plotting the ship's position using more than one method is a good practice, and those include e.g. GPS, visual bearings, radar range/bearings, and astronavigation. What is the benefit in monitoring the voyage using ICDIS? The speed and accuracy of ICDIS allow navigating officers to plan their voyages much faster than on paper charts. Most systems can import data into a spreadsheet format, which helps to reduce the manual effort of inputting waypoints. Advances in display technology have led to a new generation of electronic voyage planning stations on ships. These developments have come at the right time, as shipping transfers from preparing routes on paper charts to electronic passage planning. While ICDIS at the front of the bridge should be kept uncluttered and used primarily for voyage monitoring, there should be no limit to the information that is displayed on the planning station at the back of the bridge. The navigation station should have the latest electronic navigational charts, ENCs, installed at different ranges and scales. It should also have weather, sea state, environmental and hazard information pertaining to any planned voyage. Other information, such as port conditions and date-dependent data, plus services including weather routing and route optimization, can be installed on the planning station. All this should be integrated into a single display for preparing safe voyages that can be used by the bridge team. Since record keeping is of utmost significance and that each event occurring on board has to be best recorded for all the official and legal intentions, we shall discuss what one has to bear in mind while jotting down the entries in a few important logbooks. To maintain this statutory logbook, and the master has the overall responsibility to oversee its authenticity and appropriateness. The logbook is considered to be a running log of all official events such as arrival/departure of the vessel to/ from the port, drafts, freeboards, onboard emergency drills, crew on board, fuel/freshwater rob, masters handing over/taking over, etc. Although some flag states do provide a short guide for keeping the official logbook, and while some don't, it is imperative that all entries must be made in a professional and legible manner. Methods of position fixing. Log. Ranges. Leading lights. Running fixed positions. Estimated position. Methods of position fixing. Cross-bearing, 2 objects. Cross-bearing, cocked hat. Fixed by depth soundings. Estimation with horizon. Vertical sextant angle. Special angle fix. 4-point fix.
A traditional technique, but is very important nonetheless. Your GPS will give you a latitude and longitude, corresponding to the WGS84 datum, and this is why we wanted the datum of the chart. Some units may use a different datum, so do check the instructions for your own before plotting. In this example, at 12 o'clock noon, our GPS is telling us that we're at 43 degrees, 56.4 minutes north, 068 degrees, 03.5 minutes west. And we know latitude is the measure of how far north or south you are, so it corresponds to the side of the chart. So for us, we're looking for 43 degrees, 56.4 along the side axis. Now that we've got our first line, we know we're somewhere along the parallel line that passes through this latitude. For our second line, we use the longitude, 068 degrees, 03.5 minutes west. And this time we line it up along the bottom of the chart. Then we draw a parallel line straight up so that it crosses our first line. The GPS fix at 12 o'clock is the point where these two lines cross. And now a question for you. How many lines of position is this? Is it 2 lines of position, basically the 2 lines that we've drawn onto the chart, or is it more than 2? Vote now on the card and stay until the end of the video when I will give my answer. The next line of position that we're going to discuss is the visual bearing line. For this, you just use your boat's compass to take a bearing of an object. We're going to use the lighthouse here on Pitimanon Island in this example. You can shoot the bearing on your magnetic compass, which gives you a compass bearing, but then you need to correct it to be a true bearing before you can plot it onto the chart. Correcting a bearing just means taking variation and deviation into account. Variation is the difference between magnetic north and true north, and is to do with the magnetic north pole wandering around a little bit. Deviation is the difference between magnetic north and what your compass says is north, and is more to do with the metals on your boat deflecting the compass a little bit. So to correct a compass bearing, you just apply the corrections in order. Take your compass bearing and add a deviation correction, which you can read from your compass card. This will give you a magnetic bearing. Then you can apply variation to that magnetic bearing, which will give you your true bearing. You can find the variation on the compass rose on the chart. So you can see here in our case it's going to be 16 degrees 15 minutes west, as we're still in 2018. It sounds complex, but it's not too bad. So we get a compass bearing of 060 degrees at 1500. We can start our table adding 060 into the compass row. We then read the deviation from the deviation card. If we're currently heading north, our deviation is going to be 4 degrees west. This tells us that all magnetic compass bearings are 4 degrees west of being a magnetic bearing. So we need to subtract 4 degrees to turn it into that magnetic bearing. This gives us 56 degrees magnetic. In the same way, we already know the variation is 16 degrees 15 minutes west, so we just need to subtract 16.25 from 56, which gives 39.75. So we'll call that 40 degrees true, as the nearest whole degree is going to be fine for me today. Do please tell me in the comments below if you'd find further explanations of correcting compass bearings useful, and we can look at doing that in a future video. With our true bearing, we can then plot straight onto the chart. We'll just use the compass rose lined up with 040 and transfer that line to the lighthouse. Our line of position runs away from the lighthouse and tells us that we're somewhere along the line at a time of 1500. Theoretically, the line could extend any distance away from the lighthouse, so we indicate that potential continuation using a single arrow at the end. Next, let's look at our third way of finding a line of position, a range. There are a few different ways for finding ranges at sea. The easiest, of course, is to use your radar, but I know a lot of smaller boats may not have a radar, so let's use a sextant instead. No matter what method you use to get your range, plotting it onto the chart is exactly the same. We're going to use a vertical sextant angle. This is why I wanted to know how heights are measured on this particular chart. We'll use the same lighthouse as before, and we can see that it's 123 feet above mean high water. What this means is that when the tide is at mean high water height, the light at the top of the lighthouse is 123 feet above. The tide does change, so you may need to apply a correction, but we won't do that today. Let's just say the tide is at mean high water level. On this diagram, we are some unknown distance away from the lighthouse. We can now make a triangle formed by the lighthouse top, the sea level below, and our own position. We want to know the distance along the bottom of the triangle. That distance is x. We already know the length of the opposite side, which was 123 feet, the height of our lighthouse, and we can measure the angle at our own position using the sextant. Let's say the sextant gives an angle of 18 minutes, or 0.3 degrees. Again, I won't cover sextant use today, but let me know in the comments if that would be another useful video in the future. From trigonometry, tan of an angle equals opposite over adjacent. The angle is 0.3 degrees, the opposite is 123 feet, and the adjacent is the unknown that we're hoping to find. We can rearrange a little bit to get x equals 123 divided by tan of 0.3 degrees, which equals 23,491 feet. I've just rounded the answer off to the nearest foot here. There are 6,076 feet in a nautical mile, so this gives us 3.9 nautical miles in total. Do bear in mind that the angle must be precise. A reasonable sextant should give an accuracy of 0.1 minutes. If this angle had been 1 minute different, say 17 minutes instead of 18 minutes, the resultant distance would have been 4.1 miles instead of 3.9. Tiny change in angle gives a large change in the distance. Anyway, regardless of the method you use, you now have a range of 3.9 miles, which you need to plot onto the chart as a line of position. To measure distances and ranges on a chart, you need to use the latitude scale. The reason for this is to do with the projection method used to translate the spherical Earth's surface onto a flat chart. Just remember that you need to measure distances at the side of the chart. You set your compasses to a range of 3.9 miles, and then draw an arc centred on the lighthouse we used. This arc is your line of position. You are somewhere along this line, and actually that line could extend in either direction, so you indicate that with an arrow at each end. Again, the time is 1500, so now you have two lines of position taken at the same time. The only location that you could be where both lines are correct is the point at which they cross. This is your fix at 1500. Although the two lines technically do give a fix, you have no confirmation in case you made an error with one of your lines. You really need 3 or more position lines to confirm your fix. For method 4, we're going to have a look at a running fix. We'll do our running fix from Mount Desert Rock. You notice that it's way out at sea, so there's not much else available for taking bearings, so running fix is actually probably the best method here. We're going to say we're heading due north, 000, at a speed of 10 knots. We'll need this information shortly. First off, you plot a regular single line of position. Let's say we get a bearing of 060 degrees true at 1800. Notice I've already corrected this one to be true instead of it being a compass bearing. 12 minutes later, at 1812, we take a second bearing of the rock and find it's now bearing 120 degrees true. We can plot a second line of position at 1812. Now we've got two lines of position, but they're not taken at the same time. To be able to use them both, we need to adjust one of them to match the time of the other. This is where we apply our course and speed. In the time period between the two observations, 12 minutes, we have travelled 2 miles due north. If we transfer our original line of position north by 2 miles, the times will then match. We can take a point anywhere along the line to do the transfer. From any point we just measure 2 miles north, and then we transfer the original line to the new position. To show that it's a transferred line of position instead of a direct measurement, we add a second arrow to the end, making it a double arrow. The time for this transferred line of position is 1812, which matches our second observation. We now have two lines of position, both at the same time. The point at which they cross is our fix at 1812. You can see the transfer process reduces the accuracy of the fix. If your heading or speed is slightly off, it will introduce errors. This is one of the reasons for flagging it up with the double arrow. It highlights that the position is less accurate than it would have been if you'd have been using two primary position fixing lines. The final method that we will touch upon is a celestial fix. I can't cover the full celestial fixing procedure today, but we'll run over how to plot the result onto a chart. The principle of a celestial fix is that you guess your position, and then you measure a selection of stars or celestial bodies to find out precisely how far your guess is away from your actual position. We can plot the estimated position onto the chart as a triangle, adding a time that it applies, so we'll call it 1900 today. You then calculate a bearing and an intercept for any number of stars. For example, you may have shot Sirius, and you find its bearing 120 degrees, and you get an intercept of 1 mile towards. This means that your real position is 1 mile closer to Sirius than your initial guess was. Measuring 1 mile along the bearing line towards Sirius, you can then draw a perpendicular line of position. You could be anywhere along that line, and it could actually extend in either direction, so you're going to put an arrow at either end. Likewise, maybe you find Jupiter is bearing 180 degrees, but this time you get an intercept of 2 miles away. This means your real position is 2 miles further away from Jupiter than your initial guess was. You have to measure 2 miles away from the bearing, and then you draw your second line of position. Assuming you have taken the measurements at the same time, Your real position is simply the point at which these lines cross. Like all other methods, 2 lines really isn't enough to claim an accurate fix. Often with celestial fixing we would plan for. Let's return to the question I asked.
A line of position is a line of observation where the ship position is expected to be located anywhere along the line. On its own, a single lock cannot provide a position fix, as the ship can be located at any point along the line. The intersection of 2 position lines is a fix that is used in position fixing to identify the navigator's location.
Position fixing. All position fixing relies upon lines of position. A line of position is basically a line that you've drawn onto the chart, in the knowledge that you're somewhere along that line. The more lines you draw, the more accurate your position fix will be. All of the methods that we're going to disposition.
Ranges of 2 or more points. Ranges must be taken off the adjacent latitude scale and the relevant arc plotted on the chart using compasses. Both ends of the arcs should be marked with a single arrow, the point of intersection circled, and the time of the fix written alongside.
In continuation about range and bearing, how to plot it, I am going to show you. This is Angsa Bank beacon. You can see the beacon, it's a north cardinal mark. So, we are somewhere around this position, and it is night time. I will show you how it looks, how the flashes appear at night. This is the Pulau Angsa Bank beacon. You can see the continuous flashing. The flashing light is the beacon. It's night time, so I'll show you around. It is around 2:30 in the morning. So this is the nighttime view of the radar. You can see the Angsa Bank beacon appearing on the radar. It is exactly on the pointer. So the range and bearing of that beacon is 2.08 and 174.7. The current position is. So this is the Angsa Bank. It is a north cardinal mark and it's a fixed mark. So you can see the star here. So as per our radar, the range and bearing was 2.08 and 174.7. And GPS position was this. So let us check how the position is going to come up. So I am going to take the bearing and range from this Angsa Bank light. So it is 174.7. 174.7. I'll transfer it. And 2.08. 2.08. This is 1 mile, 2 mile, and 0.8. It's not even 0.1, so 2.08. And from the center of the star, I'll plot the position. That is my radar position. You can see this is the bearing and this is the range, this is the radar position, and my GPS lat long were 100 degree 59.87 minutes east. So 59.87, this is 59.5, 6, 7, 8 and 9. So 87 comes somewhere here. And latitude was 3 degree 22 decimals north. So 3 degree 22 is 3 degree 22, 21, 22, 3 degree 22 minutes north. So this is my GPS position. You can see the difference is less than 1 cable. There will be a small error when the bearing is in points, so that is acceptable. So this is how You will fix your position. You can see this is the radar range and bearing, and this is the GPS position. Less than one cable is the difference. So I believe you understood how to fix your position using the range and bearing from a conspicuous object using the radar.
Leading lights, also known as range lights in the United States, are a pair of light beacons used in navigation to indicate a safe passage for vessels entering a shallow or dangerous channel. They may also be used for position fixing. At night, the lights are a form of leading line that can be used for safe navigation. Leading lights and markers are usually used in the approaches to harbors or in channels where maneuvering room is very restricted,
especially in poor visibility or at night. Here we might find additional aids which could assist us in tackling this hazardous passage. Here we could find leading lights or markers. So let's get a bit closer and investigate these lights or markers. Our first leading light or marker can be found close to shore, situated quite close to sea level, sometimes even in the water. And our second leading light or marker can be found further inland and on a higher elevation. Together, these two beacons make up the start of a line which shows us which course to take so we can make safe passage into this particular area. If the two lights or markers are above each other as we view them, we are on the correct course. If we begin to drift, these markers will no longer be above each other, showing us we have to take corrective measures. As the top marker is further inshore, to correct our course, we turn towards the bottom marker to line them both up again. If the markers drift further apart, we know we have turned the wrong way. On the charts, we should see two lights, probably marked as major lights. With the added light symbol, we should be notified of the light's identification by means of color and sequence. Our first light here is an occulting light every 3 seconds. It stands 8 meters above sea level and is visible from a distance of 12 miles. Our second light is also an occulting light, but this time every 6 seconds. This light stands higher above sea level at 20 meters and is visible from a distance of 15 miles. The chart could also show the leading line. If a heading is indicated, it's important to only follow this bearing once the lights have been lined up. A similar set of lights we might see are sector lights, which also assist us in navigating tricky areas at night. With the aid of specialized lenses and other wonderful engineering skills, the color of the light is determined by the angle at which we view the light. When viewing the light dead on, we see it as white, and as we move from different angles, we can see red and green light. If we are in the safe sector, we see the light as white, and as we drift, we will leave the sector and we will see a light change. This indicates to us we have moved out of the safe sector and into the green zone. Our angle is incorrect and we need to rectify our course. By turning to port, we will again enter the safe sector and see the light as white. The same applies to drifting out on the other side. Once we venture too far away from the safe sector, we enter a zone where the light will be viewed as red. This again indicates that a change of course is needed, in this case turning to starboard. Once we have altered our course, we should return into the white zone and back into the safe sector. Let's now have a look and see what we could possibly find on a chart. We should expect to find the light indicated as a major light with the required light teardrop. As we are dealing with sector lights, we should find all the colors recorded in the light sequence along with other light information. This particular light is situated 15 meters above sea level and is visible from a distance of 32 miles.
A running fix is a method of coastal navigation position fixing. It incorporates the use of an estimated position along with bearings off of charted objects. Using bearings as well as an E.P makes this more accurate than an E.P.
3 o'clock.
This is how we plot a running fixed position. Assuming the course is 080 degrees and the speed is 8 knots or 8 nautical miles per hour, we take a bearing of 045 degrees on Alpha Rock at 0900. Now convert the compass bearings to true bearings and we plot it on the chart. After 30 minutes we take a new bearing on the same rock that reads 015 degrees. Now convert the compass bearings to true bearings and plot it on the chart along with the new time, 0930. Knowing the speed, the next step is to determine the distance that the vessel sailed from 0900 to 0930. For that we use the formula D is equal to S times T divided by 60, where D is the distance in nautical miles, S is the boat speed, and T is the time in minutes. In our case, 8 knots times 30 minutes divided by 60 equals 4 nautical miles. Using the dividers, we span a distance of 4 miles on the latitude scale, which is closest to the course line, and which runs along the sides of the chart. We applied this span on our course, placing one leg of the dividers on the 0900 LOP intercepting the course, and the other leg on the course line. Using the parallel ruler, we transfer the 0900 LOP to the blue mark. As we notice, the two LOPs intercept at the point RF. This is our running fixed position.
What is estimated position? This is the most accurate position that can be obtained by calculation and estimation only. It is derived from the DR position with allowance made for the effects of currents and tidal streams. Again, it is an approximate position only.
If we apply the set and the drift of the tide to the 1130 dead reckoning DR position, we'll have converted this position to an 1130 estimated position, EP. To work out the set, direction, and the drift, speed, of the tide, we refer to the tidal diamonds on the nautical chart, or to the tidal stream atlas. Let's assume that at that time the set is 110 degrees, which means that the direction of the tide is towards 110 degrees, and the drift is 3 knots. To apply the set, direction of the tide on the 1130 dead reckoning DR position, we place the parallel ruler on the 110 degree line of the compass rose, and transfer that line to the DR position. To apply the drift, speed of the tide on the 1130 dead reckoning DR position to our time frame, we use the formula D is equal to S times T divided by 60, where D is the distance in nautical miles, S is the tide speed, and T is the time in minutes. In our case, 3 knots times 90 minutes divided by 60 equals 4.5 nautical miles. Using the dividers, we span a distance of 4.5 miles on the latitude scale which is closest to the course line and which runs along the sides of the chart. We apply this span, placing one leg of the dividers on the 1130 DR position and the other leg on the 110 degrees tide set, marking the new position with a triangle, recording the time as 1130. This is our 1130 estimated position, EP. Using the parallel ruler, we transfer the 045 degrees course to the new 1130 estimated position, and from there we continue to plot our new positions as we progress on our route.
Method of position fixes. Celestial fix by using sextant. How do you establish a fix using celestial bodies? Measure the altitude of a second celestial body, another star, planet, the moon, etc., and do the same thing and you get another position line. Where they cross, you have your visual fix. How do you get a visual fix position? Position by visual bearing of two objects. To plot the position by visual bearings of two objects, take the bearings of both the objects simultaneously. Now draw the bearing of these objects on the charts. The point where these two bearings, position lines, intersect will be the ship's position.
Paano natin kukuhanin yung 270 degrees? Let's go to our compass rose. So, i-align lang natin yung ating triangles para maka-obtain tayo ng 270 degrees. Okay? 270 degrees. Ang gagawin nyo lang, paandarin nyo lang yung inyong triangles. So, what you're going to do, try to slide your triangle, ano? Okay. Punta tayo sa High Mousy Tau. Okay. Let's just put a line. So, itong line na to, tinatawag natin siyang LOP or line of position. So, para maka-obtain tayo ng isang fixed object, ng fixed position, kailangan natin mag-intersect o magawa pa ng isang line. So, sabi natin, yung bearing nito, yung direction niya is 270 degrees. Nakita daw natin to on our 270 degrees. Ano? Next one is Shengshan Jiao Lighthouse. So, upon checking, tinignan daw natin na nag-bear daw yung at itong Shengshan Jiao Lighthouse ng around 330 degrees or 330 degrees. Kunwari, nakita nyo gamit ang inyong navigational equipment. So, para makita natin yon at para may align natin na maayos to determine our fixed position, let's try to use this compass rose again. So, hanapin natin yung ating 330 degrees. Okay, so once na meron na, naka-obtain na tayo ng direction, slide lang ulit natin yung ating triangles. Okay? So, slide lang. Slide. Hanggang sa mag-lie siya dito sa mismong tinutukoy natin na lighthouse, which is Shengshan Jiao Lighthouse. Okay? So, let's estimate kung gaano kalaki kung gaano kahaba yung line of position na gagawin natin. So, kung mapapansin nyo class, so nakita na natin itong LOP that bears 330 degrees. So, meron tayong dalawang bearing. Unang bearing is 270 degrees, pangalawang bearing is 330 degrees. At kung saan class nag-lie or nag-intersect yung dalawang guhit, ibig sabihin, on that particular time na kinuha mo yung iyong position by the use of two bearings, this is your fixed position.
When three or more bearings are taken from a moving ship, the resulting position lines will not as a rule meet in a point, but form a triangle. This triangle is known as a cocked hat. The name cocked hat probably refers to the type of hat worn by officers in the days of sail.
Combining cross-compass bearings. A fix can be obtained by combining cross-compass bearings using a handheld compass. Assume your course is 360 degrees north and your speed is 7 knots. You're sailing near the coast and you have Lighthouse A, Lighthouse B and the Island C in sight. The time is now 10:15 and your last estimated position was at 09:30. Checking your nautical chart, you locate and identify the two lighthouses and the island. Next, take compass bearings of the three identified objects, A, B, and C, with your handheld compass. Now convert the compass bearings to true bearings by applying the correction for variation, using the formula from magnetic to true, subtract the westerly variation and add the easterly variation. Let's assume that after applying the correction, the true bearing of the lighthouse A is 0:45 degrees, the true bearing of the lighthouse B is 0:90 degrees, and the true bearing of the island C is 135 degrees.
Position line from a depth. A fix using a bearing and depth can be very useful. It is not always very accurate but is often good enough. The bearing is plotted as before, but the depth must have some allowances made to it. You then look along the bearing you have already plotted on the chart until it crosses the 10.0 m contour line. Where they cross is your fix. What is vertical sextant angle in navigation? The angle in the vertical plane between the top of, say, a moderately close lighthouse, or other prominent feature, and the sea level below it read on a sextant. Practically speaking, the arc of the sextant is a little over 60 degrees and therefore the total angle measurable is about 130 degrees. Sextant is an essential tool for celestial navigation and is used to measure the angle between the horizon and a visible object, or two objects at sea. Four-point fix, a special case of doubling the angle on the bow, in which the first bearing is 45 degrees right or left of the bow. Due to angular spread, this is the most precise isosceles fix. The 4-point bearing. This is a type of running fix in which the first bearing is taken when the object is at 4 points, 45 degrees, on the bow. When the object is on the beam, the range will be the same as the distance run since the first bearing was taken. The disadvantage of the 4-point bearing is that the range of the single object is not known until it is abeam.
Another method of taking a running fix is by doubling the angle on the bow, having in mind the properties of an isosceles triangle. This fix requires the first bearing to be less than 45 degrees from the bow. Assuming the course is 0-90 degrees and the speed is 10 knots or 10 nautical miles per hour, we take a bearing of 0-60 degrees of the Charlie radio tower at 0-900 or 30 degrees from the bow. Now convert the compass bearings to true bearings and plot it on the chart. We observe the Charlie radio tower, and when the new bearing reads 0-30 degrees or 60 degrees from the bow, we note the time 0-915. Now convert the compass bearings to true bearings and plot it on the chart. Knowing the speed, 10 knots, and the elapsed time between the two bearings, 15 minutes, we use the formula D is equal to S times T divided by 60 to calculate the sailing distance between the two bearings. In our case, that's 2.5 nautical miles per hour. As we can see, the two bearings and the course form an isosceles triangle, ABC, where sides C and B are equal. That means that the distance from the Charlie radio tower, when we took the second bearing at 0-915, was 2.5 nautical miles. Using this method, we have a bearing and a distance using only one object.
Parallel indexing is a technique used as a measure to monitor the progress of a vessel on the track and to minimize the cross-track distance and to keep vessel at a safe distance from the shoreline or rock.
I-operate yung parallel index or paano gamitin yung parallel index line, PI line sa ating ECDIS, no? So katulad ng ARPA, mayroon din silang parallel index. Okay, itong video na to para to sa mga zero knowledge sa ECDIS o gusto lang mag-review o gustong matuto. Okay? So dito sa ito palang ECDIS na to is Transas. Dito sa drop-down menu, piliin natin yung parallel index line. Yan, okay. Now, dalawa yan, 1 at saka 2. Okay? Tingnan mo, may nag-appear na. So, pag i-on ko yung number 1, hindi mo na kailangan mag-input dyan. Pwede mo ring input manually dyan, pero hindi ko na gagawin yun. Kasi pwede mong gawin dito Itong line na yan, makikita nyo parang may dot. Position mo yung cursor dyan sa may parang tuldok, magiging cross na green. Pag left click mo, magiging bold. Yung lalaki yung line, yung parallel index. Actually, yan na yung parallel index. Pwede mo na siyang i-move. So, halimbawa, may isla dito banda. So, ilagay mo siya sa gilid ng isla para ma-monitor mo yung barko kung lumalapit ba sa isla. Dahil kung yung line na yan ay papatong sa isla, ay maaaring napadpad ka na patungong isla. So, yan yung pag-adjust ng distance mula sa yung barko. At saka, kasi nga tinawag na parallel index kasi dapat parallel sa yung course line. Okay? So, parehas sila ng direction ng ating course line. Pag sinabing parallel, parehas sila ng direction. Okay? Now, right-click to deselect. Kung satisfied ka na sa distansya, pwede mo nang i-right-click para ma-deselect. Yan, nakaposition na siya. Kung gusto mong baguhin yung heading or direction niya, huwag kang mag-click doon sa tuldok. Mag-click ka kahit saan dyan sa line. Yan. Yan, nag-green na siya, nag-cross, left-click, yan, naging bold. Pag move mo, magbabago yung direction niya. Okay? Okay? So, yan. Mangyayari to pag halimbawa, iikot na siya sa isla, kakambyo na siya, halimbawa, pa-estribor. So, ipoposition mo sa next na course. Yan. Halimbawa, ganyan yung next course. Parallel sa next course. Pwede mong galawin ng ganyan. Okay? Tapos left-click para maipako. Tapos pwede mo siya ulit i-reposition gamit yung may tuldok na yun. Okay? So kahit i-move mo siya along the line, basta yung napindot mo yung una, yung parang tuldok, distansya yung i-adjust niya. Okay? So left-click para ma-position. Para pag off, i-deselect mo lang yung highlight niya at mawawala na siya. Okay? So, ganun lang pag-activate ng parallel index. Pwede mo rin gawin sa isa yan. Actually, pwede mo rin isabay ang dalawa eh. Yan o. So, pwede mong ilagay yung isa sa pabor. Yan. Pwede mong ilagay sa estribor. Okay? Pwede mong ilagay sa pabor. Iikot mo lang yung mouse, trackball. Yan. Okay, left click. And left click kung gusto mong i-reposition dyan sa may parang tuldok. Okay, so yan na yun. And, i-deselect natin, tanggalin na natin. Hindi makafocus. Tingnan nyo. Deselect, yan nawala. So, ganun lang paggamit ko eh. And sana nag-enjoy kayo sa video na to. At